Thank you very much. It's really a pleasure to be here. Thanks for inviting me, and it's so nice to see familiar faces and to be back in a way. So I'm going to present some actually work not so much on the deep learning side, but on learnability theory. And this is a lot of it is joint work with Victor Dalmau. I'll give more references later. But basically, oh, I need to switch my cursor. Yes. Basic, and also I wanted to say, like, I don't have so much experience giving presentations over Zoom, but if people want to interrupt and ask questions, that's fine with me. It's nice to feel some interaction. Otherwise, it's hard to tell. I can only hear myself. The context of this talk is example-driven, query discovery. In general, of course, it's interesting to think about example-driven discovery of structures or like declarative specifications. In this talk, I will focus on queries, but a lot of it makes sense to can ask similar questions about concepts or ontologies or schema mappings, and these are all closely related to this talk. But I will just keep it simple here and focus on queries, database queries. So the scenario is that we are trying to construct a database query from data examples. And to be a little bit more precise, let's assume that we have a database schema which is known, and we also know the arity of the query. And then we're given some data examples. And the data example for me in this talk is a database instance and a tuple, and then a sign, which is plus or minus to indicate if this is a positive or a negative example. And a query fits this example. If it's a positive example, it means that the tuple must belong to the answers. And if it's a negative example, then it means that the tuple should not belong to the answer of the query in order to fit, right? I hope this is kind of clear. So the setting is that we are given some data examples and we are trying to infer a query. Okay. Now, you might think of a workflow like this, and mostly I have to admit I put this workflow together because it will be kind of a coat hanger for all the things that I want to discuss in this talk. So it kind of fits nicely in this picture. But you could imagine that, so you start out, you have as input, you have data examples, it's like a set of data examples E, right? And you might want to try to find a query that fits those data examples. Now, it might turn out that there is no such query, then you would just fail, right? There's not much you can do. The only thing you can do is you can revisit your input examples. If the answer is yes, there is a follow-up question. That's question 2. Is this query the only query that fits these data examples? If it is, then we have a lot of confidence in this query. And so we output it, right? But if it's no, it means that there were multiple, non-equivalent queries, let's say, that would have fit the same data examples. What could be one question you might ask is, can we elicit more examples to rule out the other query so that there's only one that remains, and then we output that one, right? So again, this is kind of the slide. The purpose of the slide is to identify 3 interesting kind of algorithmic problems that I will then talk about later in this talk. Okay. So finding a fitting query, finding out if a query is uniquely characterized by a set of examples, and then eliciting more examples with the aim of identifying a query. So so the overview of this talk is that it has 2 parts. I want to talk to you about some structural aspects of the homomorphism lattice of finite structures. So this is kind of a little bit of finite model theory or graph theory, how you want to look at it. And then in the second half of this talk, I will explain how everything that that I introduce directly relates to these problems that were on the previous slide. And also, I think that this homomorphism lattice is just it's a nice topic to talk about because it's beautiful as a theory and also has other applications. And I will briefly mention at the end with Megan and Frank and Karsten, we had other applications of this in the past for different problems. Okay, so I will keep. I will assume people are familiar with structures and homomorphisms, but so I'll not define them precisely. But if we fix a finite schema S consisting of relations, symbols, and constants, and I'll explain later why the constants are important to have here too. But then by a structure, we will mean a finite relational structure. I will drop the word finite and always assume that structures are finite over the schema. And then a homomorphism from A to B, where A and B are structures. It's a function from the domain of A to the domain of B, so that for every fact of A, the image under this function is a fact of B, and the constants are preserved. Right. So this is structures and homomorphisms. And now what I meant with the homomorphism lattice is this partial order, the partial order of structures ordered by homomorphism. So less than here means that there is a homomorphism from A to B, right? If this is going to be the fundamental concept. If there's questions about this, then it would be good to ask them. So also, two structures are homomorphically equivalent if there is homomorphisms in both directions. And I will not distinguish between homomorphic equivalent structures in this talk. So that's why I can really think of this as a lattice, as I'll explain this on the next slide. If you look at the space of all these structures and it ordered by homomorphism, then for starts, there is a least element and there's a greatest element in this set. You mean a least structure and a greatest structure homomorphically. Right? This is not so hard to see. The least structure would be the structure with no facts, and also every constant denotes a different element. Okay, and the structure on top is the most specific structure in a sense, or the most informative, is the structure that has only one element, and all constants denote the same element, and all facts over that one element are in the structure. Okay, so now we have a top and a bottom element, but the next thing to see is, and so I'm explaining why I'm calling this a homomorphism lattice. A lattice really means that every two elements in the set have a least upper bound and a greatest lower bound in the homomorphism order again, right? So now this is also pretty well known, and this meet or the least upper bound of A and B is the direct product of A and B. It's just a quadratic construction where you take pairs consisting of an element of A and an element of B. And the greatest lower bound is basically, roughly speaking, disjoint union of A and B, except in the case with constants, you have to be a little bit more careful. So it's not intrinsically more difficult, but it's just a little bit more tedious to define. But this disjoint union kind of naturally extends in some way to structures with constants. Okay, so now we have a lattice. So we can even think of this now as an algebraic structure, right? Where we have this set, the underlying set of the algebra is the set of structures, and then we have this, operations on structures. This meet and this join. We have a top and we have a bottom, and so you could study like the structure of this algebraic structure of this homomorphism lattice, right? Like you could ask many questions, like which equations holds for this, but I want to introduce one more operation which is relevant here. This is kind of they call it exponentiation, or maybe it's a residual. I'm not sure exactly. My algebra background is not so strong. But for every pair of structures, A and B, we can also define a structure A exponent B, which has this this particular relationship, which that any structure homomorphically maps to A to the B, if and only if the direct product of A and B homomorphically mapped, of C and B homomorphically mapped to A. Okay, and this is one more operation that will come back in a moment. That's why I wanted to introduce it. So I just wanted to indicate that there's more natural operations besides this meet and join that you can define in this algebra, right? Okay. So very small detour, because this is also going to come back later in the talk. There's this decision problem. It's called the product homomorphism problem. It says, given a collection of structures, A1 up to AN and B, decide whether the direct product of A1 up to AN homomorphically maps to B. And it's not so hard to see. Well, the problem, of course, is why this is an interesting problem is because the direct product of A1 up to AN is exponentially large, right? And so the naive upper bound for this problem, or you mean the obvious upper bound, I would say, for this problem is non-deterministic exponential time, because to test if there is a homomorphism, you can non-deterministically guess the homomorphism, but it's an exponentially large function, right? So it's clearly in non-deterministic exponential time, and it turns out that this is in fact next time complete, which was proved by Willard for not when the schema is not fixed, and then we improved his argument for fixed schema later on. So this problem, again, not really that central, but we'll come back later in this talk, which is why I'm introducing it here. Okay, so I want to talk a little bit more about the structure of this lattice. And one interesting aspect has to do with density in the order theoretic sense, like a dense order. So if you assume for a moment for this example that the schema has one binary relation, and let's say no constants, and let's say we have these two structures, A1 and A2. A1 has just an edge, R edge from A to B, and A2 has R edge from A to B and from B to A. Okay, then in the homomorphism order, it's pretty easy to see that the bottom structure, which is the empty structure, is homomorphically strictly weaker, like has a homomorphism but not backwards, to A1, which is homomorphically strictly weaker than A2. Okay, so that I think that part should be clear to everybody. Now, interestingly, first of all, there is no structure which lies strictly in between the empty structure and A1. That's also actually very easy to see. Like if there's no, if a structure maps to A1 but not backwards, it means it must be empty. And so it must be homomorphically equivalent to the empty structure. So in a way, that means that it is a failure of density. I have a pair and there's nothing in between, right? That shows that this order, the partial order of homomorphism of structures and homomorphism, is not in general a dense order, right? But interestingly, for the structure A2, the situation is very different. For every structure below A2, we can find something which is in between, a B prime. And actually, fact 3 follows from a slight extension of a famous result of Erdős, which says that there exist graphs of arbitrarily high girth and chromatic number. The girth of a graph is the size of the smallest cycle. So if a graph has a high girth, it means it has no small cycles. And chromatic number is related to colorability. It's like the least number of colors that you need to color the graph. And Erdős's famous theorem, I guess one of the reasons why it was so famous is it was one of the first examples of what they call the probabilistic methods, where you prove the existence of certain graphs, not by a direct construction, but by proving that a certain probability is non-zero, which then non-constructively implies the existence of this graph because it has probability bigger than 0. And then later we found Nechetriel and others found constructive methods, and strengthened the result. And one strengthening of the result basically exactly implies fact 3. Okay. Now, related to this density is this notion of a frontier, and that will be an important kind of central concept in this talk. So a frontier for a set A, for a structure A, is a finite set of structures F1 up to Fn, such that each of the structure in the frontier is below. Actually, I made a typo on this slide, I see now. Every structure in this set should be strictly below A. And then for every other structure B, if B is strictly below A, then B should homomorphically map to Fi for some Fi. Again, there's a typo in item 1. It should be Fi should be strictly homomorphically weaker than A. And what this really says intuitively is that, and I try to draw this in this picture, it's like the picture of the homomorphism lattice, and you see A, and then you see like all the structures below A. And if you look at this, all the structures below A, then F1 up to Fn are like the maximal elements in there. So they separate A from all the structure which are strictly below A. Okay. And now, not every structure has a frontier. Like the structure A2 that we saw earlier has no frontier because of this density situation, right? The frontier would have to be infinite. So by definition, a frontier is a finite set of structures. Okay, so that's one interesting concept, this notion of a frontier, right? And this is, as we will see, is very relevant for unique characterizations and for learnability. Okay, and then another interesting notion is that of a duality. And so a pair of structures, F and D, form a duality pair if, and I try to draw this in this picture, which is kind of it looks like a yin-yang diagram, but you see like it's the same lattice that we were looking at all the time, but I've highlighted all the structure which are homomorphically above F and all the structure which are homomorphically below D, and they partition the entire space. And so what this means is that I wrote this in an equation as well. It says all the structure which are homomorphically above F are precisely all the structure that are not homomorphically below D. This is saying the same thing. It's saying that these two sets form a partition of the entire space, right? And you can generalize this further. This is the notion of a generalized homomorphism duality. It's like a pair of finite sets of structures. And it says that if you look at all the structure which are above some Fi, and you look at all the structure which are below some Di, then these two sets also partition the entire space. And I'll give you one example to kind of illustrate why this is an interesting concept. And then after that, we are pretty much done with the first half of the talk, and then we'll move to the learning part. But well, there's actually 2 more slides. But so one famous example of but this is not really fitting. It's actually an infinitary example of a homomorphism duality. Here I require the sets to be finite, right? But just an example is nice enough that even though it doesn't fit exactly this definition, I wanted to give it. A graph is too colorable if and only if it has no cycles of odd length. This is a famous fact from graph theory, which you can write it as a homomorphism duality. It says a graph maps to K2. So K2 is the 2-element clique. If a graph maps to K2, it means it's too colorable. That's the same thing. So it's a graph maps to K2 if and only if C 2n plus 1 does not map to G for all n, okay? And where Cn means the cycle of length n. So this is just another way it happens that we can state this theorem of graph theory as a kind of a homomorphism duality. Okay. Good. So this is the most technical content from the talk. And there's one more concept which is going to be important. It's not a difficult concept. Oh, actually, okay, I'm running ahead of myself. There's one nice thing, and I put this slide here because I was just not because it's that relevant, but because it's fun to see. Like I was saying before, we can now think of this homomorphism lattice as an algebraic structure, and you can do algebraic reasoning in this structure. And an example of this is it turns out that you can turn from any generalized homomorphism duality you can construct a frontier, and from every frontier you can construct a generalized homomorphism duality. And so in one direction this involves taking direct products, and in the other direction this involves taking exponentiation that I defined earlier. And you can prove this, and these are very elementary arguments that just use basic reasoning in this lattice, right? In this algebraic structure. So we can do algebra on this. It's like proving algebraic equations here. So I'm not going to go through the proof, and I'll not even like really go into depth about this. But for people that appreciate this, I thought it was just showing some. I don't know. I find this area really beautiful, and it's really fun to work with this lattice. Okay, so the last concept that I need to introduce is this concept, which is a variant of acyclicity, and we call this a C-acyclicity. A structure is C-acyclic if it doesn't have any cycles, except we allow for cycles that go through a constant, like go through an element named by a constant. This is a little bit informal, this definition. If I want to make it really formal, we introduce the incidence graph of a structure, which is the bipartite graph consisting of the elements and the facts. And then we say that there is no cycle in this incidence graph, except we allow for cycles that go through an element named by any cycle is okay as long as it goes through an element named by a constant symbol. Again, this turns out to be an important notion of acyclicity for this in this context. And specifically, this helps us explain when frontiers exist. So this theorem 1 says, for all structures, the following are equivalent. A has a frontier, or A is homomorphically equivalent to a C-acyclic structure. So a C-acyclic structure are the ones that have a frontier, essentially. And now we can go back to the example that we had before. If you remember A1 and A2, we had two structures, A1 and A2, and I said that A1 has a, I didn't say this explicitly, but from what I said, you can figure A1 has a frontier and A2 does not. And this was because A1 was acyclic and A2 contained a cycle, and actually it contained a bad cycle. So that explains now why in one case we were seeing this kind of density, and in other case we were not seeing that. Okay. Theorem 2 says, for C-acyclic structure, the frontier can be computed in polynomial time. And theorem 3 says, it's a corollary actually of this. It says that testing whether a given set of structures is a frontier for A is NP complete, because well, yeah, it's an easy proof from theorem 2 basically. Okay, so all of this stuff, a lot of these results, they all proved by in a bunch of papers by Neshetriel and Tardif and other people, Fonyok, and we did. My contribution here were limited, but were most importantly two things. One is they only consider graphs or relational structures without constant symbols, and so this C-acyclicity was somehow in the older work. This notion of C-acyclicity didn't quite arise in exactly this sense because there was no constant symbols. And the other thing is this can be computed in polynomial time. This is a very recent result from this year. It's actually not even published yet. but that's a result from this paper with from myself and Victor Dalmau. Okay, so there's a lot more to say about this. There's a very nice textbook, Hell and Ashetrial Graphs and Homomorphisms. So of course you can imagine that, yeah, there's this issue about the constants and everything, but if you forget about that, a lot of most of the interesting things that happen in this homomorphism lattice already happen for directed graphs, right? So that's the case that they study in this textbook. Okay, so a highly advised source of reading. Okay, so now I want to go back to example-driven schema discovery, and I already showed this slide before. So this identifies like three interesting problems. One is a kind of a fitting problem. Does there exist a fitting query for a set of examples? Two is a kind of a unique characterization problem. And three is, how to elicit more examples to identify a query. It's kind of a learning problem, as we will see. Okay, so now, for the remainder of this talk, we're going to restrict attention to the case where the query that we are trying to discover is a conjunctive query. And we can say more about other classes of queries later. But the nice thing, of course, no surprise here, is conjunctive queries are very nice to work with because they correspond to structures. Like you can view a conjunctive query as a structure. Actually, if you have a k-ary conjunctive query over schema S, really, you can equivalently think of this as a structure over the schema S expanded with constant symbols C1 to CK. And the idea is that you take the canonical structure associated to this conjunctive query, and the free variables of the query need to be marked somehow in this structure. It's important to know which elements in the structure are the free variables of the query, the answer variables. And so we use the constant symbols to mark those, right? So that's really why in the beginning of the talk I stressed that it's important to consider structure with constant symbols. Okay. Now, a conjunctive query corresponds to a structure over this expanded schema, but an example also corresponds to a structure over the same schema. And then a query fits a positive example precisely if there is a homomorphism from this query viewed as a structure to the example viewed as a structure. And the same, a Q fits a negative example if, just in case there is no homomorphism from the query viewed as a structure to the example viewed as a structure. Okay. Now, in the next couple of slides, I wanted to really keep the notation simple. So I will assume that there's no, that k is 0, that we are talking about Boolean queries, but really everything holds for a case where k is bigger than 0 too. Okay. In any case, this kind of sets the stage for applying results about the homomorphism lattice, in the present context. So again, the fitting problem is given a set of data examples, decide whether there is a conjunctive query that fits those data examples, right? I told you we're now focusing specifically on conjunctive queries. Now, there's this lemma which says that basically there's a natural candidate for a fitting conjunctive query, which is the direct product of all the positive examples in E. And it turns out that the following are equivalent. There is there is a conjunctive query that fits the data examples. 2, Q star fits the data examples. So if any query fits, then Q star fits. And really, because Q star is the direct product of the positive examples, by construction, we know that it fits the positive examples. But it might not fit the negative example. So really, and that's what item 3 says, all that you need to check is that Q star does not have a homomorphism to any negative example in E. And 4 says, in fact, if this holds, then Q star is in fact a most specific conjunctive query that fits the data examples in E. Okay, and now it's pretty clear from item 3 that in order to solve the fitting problem, it suffices to check a few instances of the product homomorphism problem, right? Like we are basically checking whether a direct product of structures maps to another structure. And so this is, in a way, this problem is clearly very closely related to the product homomorphism problem, and in fact turns out to be in certain sense equivalent. So this problem turns out to be next time complete. Okay. So now let's say that we know how to solve item 1, and let's say that we find out that indeed if the answer is no, then we are kind of in the boring branch of this diagram. So let's assume that the answer is yes, that we have this query now, right? And now we want to know if the query is the only query that fits the data examples. Okay, so really this is a uniqueness problem. We say that the examples uniquely characterize Q if Q is the only conjunctive query up to logical equivalence that fits the examples in E, right? And so the problem, the second problem is really the following problem. The input is a finite set of data examples E, and a query. In this case, we actually know that the query we constructed was already a most specific fitting conjunctive query, right? Because it was Q star that we constructed before. And we have to decide if the examples uniquely characterize this query. And now it turns out that this is very closely related to this notion of a frontier. In fact, it turns out that the examples uniquely characterize Q if and only if the negative examples in E form a frontier for Q. And so now we can leverage all the results that we have about frontiers. And in fact, I told you before that testing if something is a frontier for structure is NP complete. And indeed, we can just apply this, plug it in here, and then we get this particular unique characterization problem is NP complete. So now we see, start to see how we are exploiting these connections with the homomorphism lattice. Okay, so and now, of course, if the answer is yes, then we output Q because we know that Q is the only one that fits the examples. But if the answer is no, then we are kind of at 3, and 3 is the most difficult problem here, right? Elicit more examples until only one query remains. And the first question that arises in this setting is this question which I asked in red here is, will finitely many examples ever be enough to uniquely characterize the target conjunctive query? You know, we could elicit more and more examples, but will this ever stop? Assuming that there is some specific target conjunctive query that we are trying to infer here, then this theorem says that this target query Q is uniquely characterized by a finite set of examples if and only if it has a frontier, if and only if it is C-acyclic. So now everything comes together about frontiers, right? And so we know that if, first of all, if the target conjunctive query, that the one that we are trying to discover, was not C-acyclic, then it's hopeless, basically, because we can elicit more and more examples, but we know that, you know, it's never going to be no matter how many examples we collect, they are never going to uniquely characterize this query because this query doesn't have a unique finite characterization, right? So on the other hand, if the target query is C-acyclic, then theorem 2 says, then in fact, the class of C-acyclic conjunctive query is efficiently exactly learnable with membership queries. And I won't have time to go into the definition of this, but intuitively what this says is that if the target query is C-acyclic, then there is a polynomial time algorithm that after asking for the label of one or more examples, so it may interactively ask for, you know, labels for, you know, examples that it computes. So that means eliciting more examples, right? It terminates and identifies the correct target query modulo logical equivalence. And so theorem 2 says if the target query is acyclic, we can find it. But theorem 1 says that if in some sense if the target query is not acyclic, then it's hopeless, right? So they kind of theorem 1 and 2 kind of very nicely complement each other in that sense. Okay, so this is kind of the end. I'm close to the end of the talk. I want to say like there's much more we can say about this. I want to say one thing very briefly about unions of conjunctive queries. If you want to, so if you want to go beyond the case of conjunctive queries, and you're interested in wider classes, it's natural to consider unions of conjunctive queries. Now, it turns out that some situation is a little bit different, but similar in other ways. But in the same way that frontiers keep popping up in the conjunctive query story, the same role is played by generalized homomorphism dualities when you look at unions of conjunctive. So a unique characterization for a union of conjunctive queries corresponds precisely to a generalized homomorphism duality. And then you can play kind of the same game. I won't go through the details, but I just wanted to say some final notes because I'm running late. Main references are in these papers, which also discuss some applications to description logic and schema mappings that you can read about there. There's a lot more to say. There's quite some literature by now about learning description logic ontologies and concepts. I didn't have time to review all of this. This is an overview paper by Anna about different approaches. And the last thing I want to say is this other paper from a while back used homomorphism dualities as well, but in a completely different context. So I think we haven't quite exploited all the possible use cases of this homomorphism lattice, and I think we're bound to find some other interesting places where we can use those concepts. So that's also one of the reasons why I thought it was interesting to tell you about it. Okay, thank you very much.